For chapter 5, we're going to dive into forces a little bit more, talking about friction, drag, and elasticity. On chapter 4, we talked about our applied forces, external forces, things of that nature. For chapter 5, we're going to talk about forces that hinder motion and that can pull back a little bit on the force that is applied. And real world scenarios, we always experience some of these forces one way or another. Friction is pretty much between anything. Drag can be anything like air resistance or anything hindering any free movement of an object. So friction is a force that opposes relative motion between systems in contact. While a common force, the behavior of friction is actually very complicated and is still not completely understood. We have to rely heavily on observations for whatever understandings we can gain. However, we can still deal with its more elementary general characteristics and understand the circumstances in which it behaves. There are two primary types of friction which we will concern ourselves with. So there's static friction and kinetic friction. So while friction is a force, like they mentioned it here, we don't fully understand why exactly it happens. You have to think about it in a very small scale. When two surfaces touch, you have those interactions between atoms, those small molecules, where they're essentially touching, but not exactly. So that's why they're saying that it's not fully understood, but we do know that friction does exist between everything. So kinetic friction is the friction that arises between two objects that are in contact and moving past each other. Think of a textbook sliding across a table, or pretty much anything sliding across any type of surface. Where static friction occurs between two objects which are stationary. This time, the textbook is simply sitting on the table, not moving. So these are two different types of frictions. Like they mentioned, kinetic is, you can think of kinetic pretty much of anything that is moving across any surface. With static, it's anything that is just stationary, anything that is just sitting there. You may wonder why there are two different types of friction, because for most materials, it is harder to get an object to start moving than it is to keep it moving. We will see this when we examine the coefficients of friction. So for this figure, they try to break it apart a little bit more, where you have this crate and it's on this surface, but as you can see, that little magnification there, that's really what it looks like at a small scale. So to our eyes, you see, okay, well, it's a flat surface and the surface of the crate is flat. But if you magnify it a little bit and try to look deeper into it, you'll see that the surfaces really aren't smooth. They're more rugged than anything. And this is pretty much the case with almost every object, even though your laptop, your phones, just a flat surface can look pretty much smooth and flat. It's not pretty much the case. Now there are objects that you can tell, okay, well, yes, this is a rugged object, this is gonna have more friction, you know like concrete. You can tell that it's not all the way flat. There's little gravels in the middle of them. So there are surfaces where you can tell, but at a microscopic scale, you'll be able to see this image more than anything. So for friction forces, always oppose in motion, so they're always in the direction opposite in the motion. In order to describe the magnitude of the frictional force, we need to know the coefficient of friction between two materials. So here are the coefficient of frictions between these systems. Realize it's saying system, not just one particular object. So it signifies the static friction and the kinetic friction of all of these systems. So rubber on dry concrete, rubber on wet concrete. So you could think of these like for your shoes. When you're stepping, you have rubber on the bottom of your shoes. And whether you're on dry or wet concrete, that'll be your static friction or kinetic friction. Wood on wood, wax wood on wet snow, and so on and so forth. As you can see, like when you get to ice down here, these are significantly less than if you're on wood or metal or rubber. And we do know that ice is more slippery. It's easier to keep the motion going. Like if anybody has ever gone ice skating, you know that it's easier to ice skate and keep going in a straight line than, when you're just walking. When you're just walking, you have to continuously put force on your shoes to make you go forward. You have to keep walking. Whereas if you're ice skating, you could just skate for a couple seconds and you keep the motion going for a little bit. The frictional force is proportional to how much the two objects are touching. So the strength of the frictional force is related to the normal force. In fact, for kinetic friction, the frictional force is the F of K, so friction of the kinetic friction, equals your mu K, which is right there signified by coefficient of kinetic friction, and Fn. Fn is your normal force. Same thing for static friction here. But here you notice that the static friction needs to be less than or equal to your coefficient of friction of static friction and your normal force. Now, the reason the normal force is involved is because if you're thinking about it, anything that is on a surface, the weight, your normal force is being pushed on it. So the weight of it is pretty much holding on to that surface. So if you have, a pin on a surface, the weight of that pin is pushing down on the weight of whatever it's on. So, for example, for me right now, it's on my table. So the weight of my pin is going against the surface of the table. So if I was trying to slide the pin across, then that's where the normal force would come in contact. So the coefficient of friction I would need to look for is my pin or a pin, a plastic, against a wooden table. Since my pin isn't moving right now it's static friction. But if I were to slide it across, I will need to get the coefficient of kinetic friction for me to actually know exactly how much friction it has. So here's an example. You have a 10 kilogram box is moving to the right in the positive x direction. We have our positive x, positive y signified here, along a flat horizontal table under an applied force of 40 newtons. If the coefficient of kinetic friction between the box and the table is mu k equals 0.2, then what is the acceleration of the box in the x direction? Now I noticed that this one wasn't necessarily in the book, so I went ahead and just wrote it out here. What I did here is I wrote down everything that I knew first. So the problem tells me that it's a 10 kilogram box. Went ahead and wrote that as my mass. It tells me an applied force of 40 newtons, so I went ahead and wrote that as well. It tells me my coefficient of friction of kinetic friction is 0.2, so I wrote that as well. And I know I'm going to work with my F equals ma and my kinetic friction. So I went ahead and wrote those two formulas here. So I need to know all of my forces in the x direction. If I go here, well, I know my F force applied is to the right, which is positive, and I know my kinetic friction is to the left, opposing the motion, which is negative. So if I'm combining these two forces, I know my force applied minus my friction force would be the total forces that I need to worry about. And obviously you have equals ma, just your standard force equation. So I will go ahead and apply all my numbers. So I have 40 for my applied force. If I'm breaking this down a little bit, I know my mu k is 0.2. And then I know my normal force is pretty much my weight, which is mg, mass times zero gravity. So my mass is 10 kilograms and my gravity is 9.8. And all that equals mass times acceleration. So I know my 10 kilograms goes here. I went ahead and did this section first. This will give me 19.6. So I do 40 minus 19.6. That gives me 20.4. On the right side is still just 10. So I go ahead and divide by 10. So my acceleration here is 2.04 meters per second. Now, the reason I couldn't just do 40 equals ma, my just force equals ma, was because I knew I had to take my friction into consideration. If there wasn't a friction, if it said negligible, that friction was negligible, then yes, I would do 40 equals 10a divided by 10. So my acceleration would be 4 meters per second squared. But since there is friction, I have to make sure I incorporate that in there. So I have to make sure that this friction goes in here, but I also have to see that it's minus because it's opposing it. It's a negative friction. But that's pretty much the basis of this problem here. It's pretty much straightforward. As long as you know your two equations here and that you have to incorporate your friction along with your applied force. Everything else just kind of falls out. So for example, 5.1 in the textbook, we have a skier with a mass of 62 kilograms is sliding down a snowy slope. Find the coefficient of kinetic friction for the skier if friction is known to be 45 newtons. So here you can see that this is the total problem, and our free body diagram goes as it shows here. So we know our friction is opposing the motion of the skier going down the slope. We know to break apart our weight here because we are at an angle, 25 degrees. And we know our normal force is pointing perpendicular to the surface. So here they start off by saying, okay, well, my normal force is our perpendicular weight, which is mg cosine of 25. They go ahead and just plug it into the friction formula here directly. They don't figure out the number first. But to solve for mu k, then you just have to divide this side by mg cosine of 25. Now, if you wanted to, and it's easier for you, you can go ahead and solve for whatever number this is, mg. So the weight or the mass was 62 times 9.8 cosine of 25. Get that number first, and then just plug it into this equation here. It's easier for some people. Here they just go ahead and plug in the whole equation. But essentially, that's what you're doing. So you have mu k equals my friction force, which they told me here was 45. So I have 45 divided by the 62. Well, first of all, by the normal force. So 62 times 9.8, which is mg. And then cosine of 25 here is 0.906. So my kinetic friction is 0.082. Notice that there's no units. The coefficient of frictions don't have units. So it's just the number here. Okay. Here we have two rough surfaces in contact have a much smaller area of actual contact than their total area. When there is a greater normal force as a result of a greater applied force, the area of actual contact increases as does its friction. So if we have a small normal force, like let's say a feather, if a feather is on the ground, that would have a small normal force compared to, a textbook. Like I mentioned earlier, because the normal force is incorporated with the friction, that really does take into effect on how much contact that object, whether it's the feather or whether it's the textbook, is actually in contact with the surface. So here's a conceptual example. Which method of sliding a block of ice requires less force? Whether you push it or you pull it, or are they the same? So here you have, a force applied at this angle, and let's say you have a similar force here applied at this angle. Well, here you have a tension as well. So it might be less for the person, in this case, to pull the block of ice. But you also have to take into account, the mass of the ice, which force is applied here. So at a glance, you could say that it's neither because you don't have any numbers, you don't have any details on what the force applied is, what the mass of the ice is, or any of that stuff, any of the accelerations. If you have all that, then you can kind of guesstimate that whether it's the force applied, which is pushing, or the force applied whether it's pulling here. Okay, so now we are moving on to drag. Another interesting force in everyday life is the force of drag on an object when it is moving in a fluid, with either a gas or a liquid. You feel the drag force when you move forward your hand through water. You might also feel it if you move your hand through a strong wind. Like friction, the drag force always opposes the motion of an object. Unlike simple friction, the drag force is proportional to some function of the velocity of the object in that fluid. The faster you move your hand, the harder it is to move. You also feel a smaller drag force when you tilt your head or your hand, so only the side goes through the air. You have decreased the area of your hand that faces the direction of motion. So if you're driving and you have your hand out the window, you've noticed if your hand is straight forward, it's less likely to move, whether it's if your hand is facing perpendicular to the wind or to the motion you are going in, then your hand experiences more of that drag force. Same thing if you're like skydiving. Obviously, if you're going straight down, you're going to feel that drag trying to keep you up there. But, obviously gravity is going to push you down. So for 5.10, we have bodysuits such as LZR Racer Suit have been credited with many world records after their release in 2008. Smoother skin and more compression forces on a swimmer's body provide at least 10% less drag. So obviously the surfaces, in this case the bodysuits, having contact with the water, it's smoother, so the drag force is less. Drag force, which is FD, is found to be proportional to the square of the speed of the object. So that basically means FD is proportional to velocity squared. And we can go ahead and say the FD equals 1/2 C rho A B squared, where C is the drag coefficient, A is the area of an object facing the fluid, and rho is the density of the fluid. Some interesting situations connected to Newton's second law occur when considering the effects of drag forces upon a moving object. So it makes sense for us to know that we have to have a drag coefficient because we have a coefficient of kinetic friction or static friction. We have to have something there. We need to know the density of the fluid, which is why rho is there. And obviously, if you're making contact with that force, with that drag force, you need to have an area of the object that is actually in contact with that force. You can go back to the hand example. If it's straight line with the wind, you won't feel it as much, whereas you turn it and your palm is facing the wind, then you feel it more. Consider a skydiver falling through air under the influence of gravity. The two forces acting on him are the force of gravity and the drag force, ignoring the buoyant force. The downward force of gravity remains constant regardless of the velocity at which the person is moving. However, as the person's velocity increases, the magnitude of the drag force increases until the magnitude of the drag force is equal to the gravitational force, thus producing the net force of 0. A 0 net force means that there is no acceleration as given by Newton's second law. At this point, the person's velocity remains constant, and we say that the person has reached its terminal velocity, so the fastest that person can possibly go. Okay, so for example, 5.2, find the terminal velocity of an 85 kilogram skydiver falling in the spread eagle position. Assume the density of air is 1.21 kilograms per meter cubed, and the drag coefficient is C equals 0.70. This one is back in our textbooks. Okay, so if we're looking for the terminal velocity, as we mentioned in the slide before, that means our net force is 0 because that's where the forces equal each other out. So thus we use mg, which is just the force of gravity acting on them, equals 1/2 rho CAV squared, as shown here. And if we're looking for a velocity, then we have to rearrange this equation here. So first thing I would do is multiply each side by 2, right? Because you have this 1/2, you need to get rid of it because your velocity here needs to be by itself. So multiply each side by 2, which is where this 2 comes from. Then divide each side by the rho CA. So that's why you divide it over here, and it's at the bottom over here. And to get rid of a square, you have to square root. So that's where this square root comes from. Then after that, you plug everything in. You know that your area must be 2 meters times 0.35. That is in the spread eagle position. So that gives us our area, which is 0.70 meters squared. Plug it all in here and you get a terminal velocity of 44 meters per second. That is the terminal velocity for this person here. All right, and for this section, we will not talk about 5.3. We will omit that section here. And lastly, I've added some problems here, simply just to go over as practice problems. The setups are pretty straightforward, like number 1 here. 63 kilogram sprinter starts a race with an acceleration of 4.2. What is the net external force on him? You obviously have an applied force. You have your mass times the acceleration there. And you have to remember your coefficient of, or your friction force. So the contact here would be the rubber shoes that he's wearing on concrete. So you need to go back to the chart here. So you can say rubber on dry concrete. And we are talking about he started a finish race, so we're going to talk about kinetic friction here. Same thing for number 2. Number 2 is really just more of a force problem. So the weight of an astronaut plus his spacesuit on the moon is only 250 newtons. How much do they weigh on Earth? What is the mass on the moon and on Earth? So remember, mass doesn't really change, so the mass should be the same on moon and on the Earth. The only difference here is that you have your force of gravity. Gravity on the moon is different than our Earth gravity, which is 9.8. It's less than that. And that's really the only substitution we have here. For number 3, just wanted to go over that one briefly. You have 2 children pushing horizontally on this one child in the middle on the wagon. The first exerts a force of 75 newtons. The second, 90 newtons. So obviously the second force is greater. And you have a friction force of 12. So you have to make sure you draw this correctly and know what system you're talking about. Obviously, the system is the third child on the wagon. So you have a force pushing it, let's say, to the right at 75 newtons. Another force pushing it to the left at 90 newtons. So obviously, the third child's going to go more to the left because that has a greater force. But its friction force is going to be pointing to the right, right? Because it has a friction of 12. So you have to draw your free body diagram. First of all, your system of interest is the third child on the wagon. You draw your free body diagram showing all the forces. So you have one force to the left of 90 newtons, one force to the right of 75 newtons, and then another force to the right of 12 newtons. And then you calculate your acceleration similar to the example that we went over with the 10 kilogram box. And what is the acceleration if the friction were changed from 12 to 15 as a simple substitution there. And for number 4, suppose a 60 kilogram gymnast climbs a rope. What is the tension on the rope if he climbs at a constant speed? So constant speed means my acceleration is 0 because my speed is not changing. Now, then you really don't have to worry about your force of gravity there. And what is the tension on the rope if he accelerates upward at 1.5? So then now you have an acceleration here. So you can go through these other 2 slides here. Just wanted to include some practice problems here for this chapter. If you have any questions over the chapter, please be mindful to contact me.